Okay, we're going to be looking at section 9.4 for us about mathematical induction. This is something we talked about with the A3 class the other day. I do believe it was Friday. It's kind of a difficult lesson to just kind of to talk about. Keep in mind, mathematical induction is a form of proof. So you're talking about a logical um, method of thinking. You're trying to prove um, a set of integers or set of data exist. So there's three. You can think of it as three little statements exist. Typically with the textbooks and all, they break it down into two. I like to think of it as three, but whichever one works for you. The way this works, it says let P sub n be a statement involving positive integers n. So you're going to have something. Lots of times they start it with S sub n. And the first thing you have to do is prove that it is true for P sub 1, or lots of times for us it's going to be S sub 1. So you're going to substitute a 1 in, and you're going to prove that that is true. And that's going to be step 1. Step 2 will be that you're going to prove that it is true for every positive integer k. So that is the next part right there. So part 2, prove that it's true for every integer k. Now that piece of the puzzle right there looks very simplistic because it's almost like you're basically just changing your variables is the way it looks. The next part is where it gets very intense with your algebraic representation and your manipulation. This is where you're going to prove that it is true for your next term, your k sub 1. So, excuse me, your k plus 1 term. So the very next term. So if you can prove that it's true for the next term, that's where the value is really at. And then that's where the intensity is. So I would say this is step 1, this is step 2, and this is step 3, and that's really where the goodie is. Now, I'm going to change a little bit about how we write it, and I'm hoping that just this little change in the notation will help you guys understand it. Now, we are going to back up just like we did in class the other day. Just as a preface to get started, we do need to practice just getting used to writing the k sub 1 term. I did forget to drop my subscripts on these. So all that these problems are asking us to do is to come up with the k sub 1 term. I keep saying k sub 1 term, but your k plus 1 term. So if you're giving this representation, if you're wanting to know what k plus 1 is, you're going to come in here and everywhere you find k, you're going to substitute the k with k plus 1. Now, your use of grouping symbols is going to be extremely valuable. So if you already have parentheses in your problem, I highly suggest that you change them to brackets. And wherever you have a k, introduce parentheses. So this first k, let it be k plus 1 and put the square on the outside. Now you already have parentheses here. So let that turn into brackets. And let the k become parentheses with k plus 1 inside. Now this little plus 1 is still out here, and the square is outside. All of that is in the numerator, the 4 is in the bottom. Now you can clean it up just a little bit, not a whole lot. You have k plus 1 out front, quantity squared, and then on the back you have the k plus 1 and then the plus 1. There is nothing that really prevents you from combining your constant terms here. You don't have a power in here, nor do you have any products. So you can go ahead and combine these two ones, and that's going to give you k plus 2, and that will be quantity squared. If you wanted to go ahead and revert that back to parentheses, you could. That's about as simplistic as you could be. Okay, that gives you an idea of what that would look like. We're not going to do all of these. We're just kind of getting the idea. So let's just do one more just to play around. If we took this last one just to get the k plus 1 term, everything on the beginning is the same. You can't change the first terms of a sequence. And you're not going to be able to change any prior terms. So all of these terms here, there's nothing you can do about these terms. They are what they are. This term is what it is. What you're trying to do is you're trying to create the next term in the sequence. So all of these exist. You're trying to create the next one by plugging in k plus 1 in the place of k. So in this last little term, and you know it's the term because it's wherever your plus or minus signs exist. So in the sequence, it's wherever your little plus signs are. You're going to come in here and you're going to replace the k with k plus 1. So again, if you already have parentheses, replace it with brackets. And then wherever your k is, put k plus 1. And then you can clean it up. Now, all this other stuff, just keep it. You will find out why here in a little bit, but it is valuable. You cannot throw it away. It is part of your sequence. All you can do over here is a little bit of cleaning. Okay? And again, keep your sequence. Later on, we'll do a little bit of manipulation to help clean this up. But we're not ready for it just yet. So the only thing that we're going to have here is 4k plus 1. And that right there is going to be representative of the k plus 1 term. Okay. Now I think we're ready for the idea of mathematical induction. Let's go for this right here. And I think what messed us up on Friday when we looked at it was that this was the way that it was written in our textbook, and that caused a problem. And as I've investigated this, different books have different representation, and this one's just not a good one for us. What will work better is what I have found in different books. Take that and put it down here at the end. Then what we're going to be working at, keep in mind this is a proof. You are proving that this statement is true. So instead of it looking like two separate things, now you actually have something that looks like an algebraic statement. So you're looking at all of this equal to this side. So you've got a left side, you've got a right side, and you're proving that they're equivalent. Okay? That's the way we're going to get started with this. This one's not going to be that bad. We've got 4 minutes. I think we can get done with this one in 4 minutes. First thing, we're going to prove that it is true for S sub 1. So, if you put in a 1, now keep in mind, when you do that, you're basically using this portion and this portion. You'll put in a 1 for the left side, and then you will put in a 1 for the right side. Prove that they are equivalent. Just don't cross over. The left side stays over here, and the right side stays over here, and just prove that they're equal to each other. When you do, you have fulfilled that duty. Okay? Now, go to the next portion. Okay? Again, let's change this notation. N squared. Now, the next part is to assume that it is true for all k. So we're going to come in here and we're going to find out what is S sub k. Well, as I told you before, you basically have your entire sequence. You're going to copy the sequence, and wherever you have an N, you're going to replace your N with a K. And that's all that is. Don't make it harder than it is. Now, here's the next part. What you're going to do, and this is where the goodie is, you have to prove that this is true for the next term, for the k plus 1 term. So, what this involves is on this left part, where you actually have the sequence. You're going to write your sequence just like it is, blah, 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 and you're going to write the 2k minus 1, but you're going to add your k plus 1 term. So you have to add the k plus 1 term here on the left side. So add k plus 1 term on the left. So we're going to stick them in here just like we did before. 2 k plus 1 minus 1. Now on the right side, you're going to take this little, it's almost like a formula, and we're going to plug in k plus 1. Now what we're after is we want to prove, using algebra, that all of this stuff on the left is equivalent to this little bitty tiny thing on the right. Okay? Now the good thing about what's on the left is that we have all this stuff right up here from 1 all the way through 2k minus 1. All of that we know is equivalent to k squared. So there he is. Remember, we copied it. It's almost like copying and pasting. So I can swap every bit of that for k squared. So that's the first order of business, is swap. That all becomes k squared. Then I'm going to take this part and multiply it out. 2k plus 2, and then bring down my minus 1. Now on the right side, multiply it out like normal. K squared plus 2k plus 1. Remember, square the first, twice the product, square the last. Clean up this side. K squared plus 2k plus 1. And look at that. It's perfect. They're exactly the same. You fulfilled your proof. That's mathematical induction. You proved that it's true for the next term for k plus 1. That's how it works. Hopefully that setup is a little bit better. We're going to try it with some other terms, with some other functions. So hang on and we'll add some more videos.